Section 2.4 deals with a very important concept in mathematics and very important concept in calculus in particular. That's the concept of continuity. And by continuity, what we mean is a very simple definition. We say that a function f is continuous at a particular number a. So at a particular point a, our function is continuous if the limit of the function as x approaches that point a is equal to the function itself at a. So as the book indicates, that implies three things. One is that the function is defined at a. Two, the limit of the function exists as x approaches a. And three, that those two things are the same. The limit as the function x approaches a is equal to the function itself evaluated at a. And what this means basically graphically is that when you draw the graph and you go through the point where x is equal to a, you don't have to pick up your pencil. It's a nice smooth graph where you don't pick up your pencil at all, no gaps or holes or anything. And so to illustrate this a little further, let's look at number 3 out of your book, where it asks you to, first of all, given this graph here, define where the function is discontinuous, any points of discontinuities. Well, you can see right away here that at x equals -4, we have a discontinuity. This is what's called the removable discontinuity, because basically you can see this discontinuity, you can think of it as basically somebody came along and just plucked that point right out of there. It's a removable discontinuity. You could put a point right in. If you were just to sketch a point in there, well, now you've taken out that discontinuity and it's continuous. All right, what about, well, yeah, x equals -2. That's another removable discontinuity. But it's also actually actually this is more better. Actually, we would say this is a jump discontinuity, not a removable, but a jump discontinuity, because we are moving along here, we get to the point, and then we jump down to a new y value. So that's a jump discontinuity at -2. Now we don't have to pick up our pencil as we come along here and come down here. Until we get to x equals 2, we have another jump discontinuity. Right before we get to 2, we jump up so that the function value at 2 is way up here. So x equals 2, that's another jump discontinuity. And now jumping up here, then we come down, smooth, smooth, smooth. Don't have to pick up our pencil, so continuous. Here we have another jump discontinuity up to -4. And actually we could think of this as this type of jump in discontinuity as an infinite discontinuity at x equals 4 is infinite, because we can assume that the function here goes off to -infinity as x approaches 4 from the left. So the limit of f as x approaches 4 from the left is actually going to be -infinity. But and to get to 4, we're going to jump up here and be defined at 4 right here. So we do have a discontinuity at 4. We call that an infinite discontinuity. And it looks like that's it. Then once we jump up here, we're continuous from there on out. Now part B asks us at which of these functions is, which of these points, these discontinuities, is the function continuous from the right or from the left? And so we have a couple other definitions we need to get in here before we can answer part B. We say that f is continuous from the right at a if the limit as x approaches a from the right of the function is equal to the function value at a. So if we look at these points here, well, it's not going to be, one thing we have to have is our function being defined at that point. So is the function continuous from the right at -4? Well, it's not, because the function is not defined at all at -4. How about at -2? As we approach from the right, does the function value equal the limit? Now the limit as we come to this point is going to be this y value, but the actual function value is this y value. So that's not going to be the case there. How about at +2? Is +2 continuous from the right? Well, as we approach it from the right, the limit is equal to the function value, because the function is defined where the limit is defined. And those two things are the same. So x equals 2 is one of the points where f is continuous from the right. And also you can see at x equals 4, as we approach from the right here, the limiting value, the value of the function that it's approaching, is equal to the actual value of the function at 4. So x equals 2 and x equals 4 are 2 points where f is continuous from the right. How about our definition of f being continuous from the left? Well, just as you might guess, it's from the continuous from the left, as you read in your book, if the limit as x approaches a from the left of f of x is equal to f of a. So as we come in from the left, again, not at -4, it's not defined there, but at -2 we are continuous from the left, because the function value is equal to the limit value as we approach -2 from the left. Any other points here? Let's see. How about at +2? No, they're not continuous from the left there, because the function value is, the limit value is down here, whereas the function value is up here at -2. And that's, looks like that's about it, not at 4. And so just -2 is the only point for which f is continuous from the left. Next thing we want to look at is a definition, and this is definition 3 on page 119. We said that a function f is going to be continuous on an interval. And what we mean by that, of course, is just what you would think if it's continuous at every number in the interval. And that is an important definition. We'll see why in a little bit. But for right now, let's go ahead and look at the next theorem, which is Theorem 4, which is at the top of page 120 in your book. And that just says basically that some nice things happen with continuous functions. If two functions are continuous, then the operations to get you new functions will also be continuous. For example, what this theorem says is if we have two functions, f and g, they're continuous at some point a, and then c is some constant, well then the following functions are going to be continuous at a. In other words, all the functions that you can make with those operations we talked about, addition, subtraction, multiplication, and division, are also going to be continuous. For example, the function f plus g is going to be continuous at a. The function f minus g will be continuous at a. The function some constant times the original function f, or some constant times the original function g, will both be continuous at the point a. If you multiply the two functions together, f times g, you will have another continuous function. And if you take f divided by g, you will be continuous as long as that point g of a is not equal to 0, because you can only be continuous where you're defined, and the function is not defined where the denominator is 0 for a rational function. So you do have to make sure that the value of g of a is not 0 to be continuous at a for f divided by g. But this is a really nice theorem because basically it says if we know one function is continuous or two functions are continuous, then when we combine those in any way, the resulting function will also be continuous. That's the kind of theorem that could save us some time. The next theorem comes about as a direct result of the direct substitution property. Remember what the direct substitution property says. It said that if f is a polynomial or a rational function, and a is a point that's in the domain of that function, so it's always going to be in the domain of the polynomial, and it'll be in the domain of the rational function as long as it doesn't make the denominator 0, then what's true in our direct substitution property, the limit as x approaches a of f of x is exactly equal to f of a. This again was the direct substitution property from 2.3. Well, that's our definition right here. This exactly is our definition for continuity. So the theorem says that if we write the theorem here based on the direct substitution property, we could say that if f is a polynomial or a rational function, f is continuous on its domain. So the point is here that most functions actually are going to be continuous. Most functions that we deal with are going to be continuous on their domain. Wherever they are defined, they're going to be continuous. The exception is going to be functions that are not continuous where they are defined. But most functions that we come across and most functions that we deal with are going to be continuous wherever they are defined. Their discontinuities will only be at places where their domain does not exist, or that are not a part of their domain. And that's what you see in Theorem 7, which I'm not going to write out here, but you need to look at that on page 122. It lists all the type of functions where the functions are continuous at every number in their domain. And as I said, most functions that we come across are going to have this property, such as polynomials, rational functions, root functions, trig functions, inverse trig functions, exponential functions, and log functions. Those are just about all the different types of functions that we will be dealing with. So as we said, most functions we come across are going to be continuous everywhere on their domain. The key is going to be making sure that we know what their domain is. Finally then, well, not exactly finally, but the next thing we want to look at is the theorems from Theorem 8 and Theorem 9 on page 123. We said that if we had two functions f and g that were continuous, then when we combine those two functions by addition, subtraction, multiplication, or division, we get a new function which is continuous. Well, remember that there is another way to combine two functions, and that is with composition. And Theorems 8 and 9 basically say that the composition of two functions which are continuous at a point are also going to be continuous. Let's just look at Theorem 9. It says that we have a function g which is continuous at a and f which is continuous at g of a, then f composed with g is continuous at a. And the proof is going to be pretty straightforward. In fact, we can just outline it here real quick. What we need to show is that the limit as x approaches a of f composed with g of x is going to equal f composed with g of a. Well, this is going to equal the limit as x approaches a of f of g of x. Now by Theorem 8, that's the theorem we skipped over, but that says basically that you can take the limit and put it inside the composite. So this is going to be f of the limit as x approaches a of g of x. Well, g is continuous at a, which means by definition that the limit as x approaches a of g of x is going to be precisely g of a. We're also told that f is continuous at g of a. F is continuous at g of a means that what we have here basically says what we have already, that this is equal to what we said, that the limit as x approaches a of f of g of x is equal to f of g of a, since f is continuous at g of a. We've gotten to the point, though, that we needed to already. We're kind of going in circles now, but this is what we needed to say, that the limit as x approaches a of f composed with g of x is equal to f of g of a, or we can write that as f composed with g of a. And so the limit as x approaches a of a function is equal to the function evaluated at that point. That's the definition of continuity. So we do have that f composed with g is continuous at a. Last topic to talk about then in this section, before we start looking at some more examples, is the intermediate value theorem. The intermediate value theorem is basically a pretty straightforward theorem. Here's what it says. Let's suppose we have some function f of x, and we know that for this function here that we have f of a here, this is a, and let's say here is b, and this value right here is f of b. So we have a function, and let's say this function is continuous. So we know that f is continuous. Basically what it says is that if you give me any number, and they call it n, so you give me any number n between f of a and f of b, any number on the y-axis between those two values, well then there's going to be somewhere along here, and maybe more than one place, between a and b on my x-axis, where my function at that point, in fact there's 3 in this particular example, where f of these values is equal to n. In other words, what it says is if we're going to go from f of a to f of b, and our function's continuous, you give me some number between f of a and f of b, we're going to have to cross that number because the function is continuous, because we're not allowed to pick up our pencil anywhere as we graph it. So let's just state it a little bit more formally. So again, it just says, we suppose we have a continuous function f, and that we have two values, f of a and f of b, and that they're different, just like in our picture here. You pick any value in between f of a and f of b, and what this theorem says is that there's going to be some number c in that interval between a and b here, so at least one number c, maybe more, such that the function evaluated at that point c is equal to n. That's the intermediate value theorem. Alright, that's it for this lecture. We will look at some more examples in the next lecture.